how are the rest of y'all's classes going? Most of you are all first year, right? So, everything else going smoothly?
Yeah.
Yeah. All right. So. Yeah, I think we've got a theorem on that through here. Right, so the last thing we were talking about was this condition on a group to be isomorphic to a collection of, well, I'm sorry, a group to be isomorphic to a collection of subgroups. And so, yeah, these following conditions. We had a collection of normal subgroups of G such that, number one, G is generated by this. And number two, that for all K in the index set, if you look at NK, you look at the case one of these normal subgroups, and you intersect it with the group generated by all the others, the identity. Under these conditions, we have the G is isomorphic to the coproduct of these normal subgroups. And actually, we kind of demonstrated an example of this. Actually, we did a direct sum, but it's okay. We also noticed that last time we had that I and J are different indices. A is in I, B is in J, then AB. So if you have something in NI, something in J, they commute. Again, word of caution, this doesn't mean that the elements of NI commute among themselves. It's just elements of NI commute with elements of NJ. Okay, so let's get down to this. And recall what this means is that each AI is in NI and AI equals 0 almost everywhere. And remember, in an algebra class or a number theory class, almost everywhere means all but finitely many. Okay. But I'm 0 in I, the subset subset AI, EI. So this is a notation. I should perhaps also subscript it with the element A, but given the sequence AI, given the sequence AI, I0 is a subset, the index set, where the coordinates are not the identity. And notice that I0 is a finite set, right? Because of the fact that this is a coproduct. And so what I'm going to do here is I'm going to let B map the coproduct to G in the following fashion. I want B this is going to be sort of a similar theme to what I did in the direct sum. This is going to be the product of AI and I0. So really, all I'm doing is I'm reading the coordinates that are not the identity, and I'm just multiplying those. That's essentially all it's happening. Just read in order all the non-identity in whatever order this is in. Now, I guess really the reason, and this is kind of tricky, why is this a homomorphism? Well, notice that this is phi. Now, somehow I need to show that it breaks up as a product like this. Right? I know. Well, I0 will be the index of non-identity entries for AI, and J0 be non-identity. Notice that all non-identity of AI are contained by the way, this containment could be proper, correct? Anybody tell me, how could it be proper? Well, for example, one of the things that could happen, this is probably the most glaring example, is each VI could be the inverse of AI. And if that happens, then all of a sudden this has no non-identity entries, right? Everybody agree with that? So if every one of these cancels, so what this is I0 union J0, that's a worst case scenario, right? And this is still, of course, finite. So the output should be am I okay with it? And of course, even if some of these are the identity, it doesn't matter, right? Because they're still implementing. Now, this is actually product. Uh-oh, how can I do that?
because elements from different normals of the system. So
So this is phi AI. Phi AI. Right. And that's really the trickiest part, because once you know that this is a homomorphism, well, once you've got that, it's easy to see it's a homomorphism just by the rules we got here. Now, the next thing I want to do, I guess I want to leave this homomorphism up here, is I want to convince you all that this is onto. Well, no. G can be written as where each AI is an NI. This is because we assume that G is generated by the union of these NIs. Right? That's where we're using this business right here. So what this means is anything in G can be made of a word out of the NIs or their inverses, but I'll just call them NIs as well because these are all subgroups. Right? And it's important to remember again, because these things commute, if they're in different normal subgroups, if I get them all out of order, if I get N1, N2, N3, N1, then I can group all the N1s together by just permuting. So I can write G more formally is equal to phi of the sequence AI, where AI equals E if I is not infinite in such above. So what this means, of course, is that phi is on. So now what we have is everything in G can be written as a product of things out of each of these normal subgroups. And so I can build something in the direct product that goes to it, or I'm sorry, in the co-product that goes to it, by just taking the identity at every index that wasn't used here. Okay, so far. Well, I guess that leaves us with 1 to 1. Right? Now we show and at this end, let's suppose that the sequence AI is an internal thing. And of course, what we want to do is show that this thing has to be the identity, and then we'll be happy because it's 1 to 1. So now I know that this product is finite. So just for convenience of notation, I'm going to write this as A1, A2 up to AN. If I really wanted to be super anal about it, I would write A IS1, A IS2, but let's just make it a little easier. We know that this finite product is the identity, and here I will assume that these AIs are all in different normal subgroups, otherwise I would have grouped them together. And now I'm going to just tear this up inductively. and show that all these AIs are the identity, and I'll be done. Notice that A1, A2, AN equals E. And this means that A1 inverse correct. Now notice that this is in M1, it's 1, but it's also in, we're generating back into M3 and little n. Right, because this is in N2, this is in N3, and this is in N. So this A inverse is the inverse of something in N1, but it's also equal to this, so it's in this. And so remember, our other hypothesis is that's the identity. Therefore, A1 inverse equals the identity. So A1 is the identity. And now we shorten it by induction. A1, A2, A1, all of the identity. So the sequence AI identity and P is 1 part. And that establishes the theory. Okay, any questions on that? Questions on that? Okay.
I have a question for the intersection of N1 with the generated cohort N2 for N is equal to D. And so, I mean, in the theorem, this is NK, the intersection of NK with all the generating group by all the NK except for N1. I mean, here, do you think I is finite?
Oh, it doesn't need to be, because certainly this right here is contained in the union of N, I equal not K.
Okay, so yeah, if it's contained in that that group, I mean, so for that G, I mean, why G is a finite? I mean, it should be the
Okay,
infinite.
I think I see just your correct question, because one of our assumptions is this, that G is generated by, I guess, it certainly may not be infinite, right? But what that means is, imagine the union of all these, it's a big set. Every element G is a finite word. You only use finitely many of these letters at a time, right? So even though there may be infinitely many of these NIs, to make any particular element, you only use finitely many of them at a time, right? That's what it means to be generated by this set. So imagine this is a big set of letters, right? And the elements of G are words that you make out of those letters. And we're fixing to talk about free groups. I'll make that a little bit more concrete, but every element of these NIs are just a bunch of letters thrown together. Every G is a finite word. You're not allowed infinitely many letters in a particular element.
Oh, yes, that's right. Thank you.
Okay, other questions? Okay. Here's a couple of corollaries. This one's nice to know. Corollary 348. Let Ni all be normal in G, and suppose E is the product So just like this situation above, and I'll tell you, I'll make it a little bit more precise what I mean by co-product in just a minute. This I need to phrase this right. Let me start a sentence here. G is the internal co-product if and only if every G in D can be expressed uniquely as in I1, in I2, in IK, where each in IJ is one of the normal subgroups, and IJ is not equal to IL for J between 1 and K, or L. So in other words, what you get in the co-product is not only can you express everything as a product of elements of these normal subgroups, but there's only one way to do it. That expression is unique. What do I mean by internal and external? Don't make too much of a big deal out of this. So is Z2 and K is Z3, then Z2 direct sum Z3 is external direct sum. That is to say, here are my Legos and I just stick them together. Right, an external direct sum is I'm given the sum as I put it together and I make the sum. What do I mean by internal? By the way, anybody know what Z2 sum Z3 is isomorphic to? It's isomorphic to Z6, the cyclic one. Now, I could have started off with Z6. And here I will write this as the internal direct sum of two of its subgroups. Here's one subgroup. And here's another subgroup. What's true about these two subgroups, 0,3 and 0,24? They intersect only in the identity. And when you put them together, you get everything. Because if you've got 3 and 4, then 3 plus 4 is 7, which is 1. And now once you've got 1, you got everything. And notice you can write Z6 as the internal direct sum of the subgroup 0,3, 0, 2. So internal means I dug the subgroups out to write it as a direct sum. Okay. Let me give you one more theorem and corollary, and then we'll talk about free groups a little bit. Theorem 349. Let Fi from Gi to Hi be homomorphisms. So this is just some big fat collection of homomorphisms. And F this is a definition. I'm going to define F to be this product of Fi, and I'm going to tell you how it works. It goes from the direct product of Gi to the direct product of Hi. And the way it's gonna work is F of the sequence GI. I guess you might be able to guess how this works. Is sequence of Fi GI, you draw an H. Okay, so this is sort of in a certain sense kind of a natural homomorphism. I've got a whole bunch of homomorphisms, each GI to HI. And what I've done is I've sort of glued this together into this big sort of master homomorphism that goes from the direct product. And what it does is the way it does its business is it just takes every little one on the appropriate coordinate. Now, here's some things about this homomorphism. F is a homomorphism. It's really just pretty straightforward to check because each separate piece is. F is a homomorphism, and F co-product. So if you restrict down to co-product, which is a subgroup, this is contained in co-product of the HIs. And the kernel of F, another factoid, is equal to the direct product of the kernel of Fi's. The image of F is the direct product of the image of Fi's. So F is 1-to-1 and onto if and only if each Fi. So there's a lot of words in this theorem, but it's not difficult to prove. So I'll leave this one as an exercise. Prove this homomorphism is routine. This is just a routine checkup section name. I'll give you kind of corollary for fun. Let Ni and Gi be families of groups. With Ni always normal and Gi. Number A, the direct product of Ni is normal and the direct product of Gi. And so, of course, whenever you have a normal subgroup, you can mod out by the direct product of Gi modulo the direct product of Ni. What do you hope? And the same thing is true for the co-product. Yeah, I'll do that for the co-product of Ni. So, let's do a quick proof of A. And I think that once you see how to do A, you'll see how to do B. This smells like the first isomorphism theorem, most definitely, right? So what I would do here is, let's see here. Oh, well, I guess I need to prove that first too, right? So if well, I got to conjugate this, right? And so let me go quickly here. I mean, this is the same thing as this is GI inverse, right? Everybody cool with that? And of course, each NI is normal. So this is in direct product. So that gives you the normality. So we've got that off of the list. Now, what I want to do here is, I think I want to do, let F go from the direct product of GI Now, I might as well use my previous theorem here. I'm going to define F. If pi goes from GI, NI, this is the projection epimorphism. This is just a function that takes GI to GI mod NI just by taking G to G NI. Right? Then we define F with product pi I. Use the notation I use the theorem. Now, according to 349, the kernel of F is the kernel of product I. See, according to this, it should be the product of all the kernels. Well, we all know that the kernel of this projection map is precisely NI. Right? So F is onto, that's also from this theorem as well, because each pi I is onto with kernel equal to the direct product NI. So the direct product of GI modulo the kernel is isomorphic to the direct product of GI. And the result of coproduct level is pretty much the same. Okay. Any questions? Questions on that?
Can you just say again how you got that the conclusion of F is onto with the kernel of?
How about, you're okay with that? You're okay with the kernel as the product? It's just, why is it on to, right?
Yeah.
Well, because, well, I can do the statement here. Actually, I could have stated this more generally, F is one-to-one and onto, if and only each FI has, and these are clearly onto, but I'll show you. I'll show you concretely. So why is this onto? Because a typical element of this, actually, I'll do it over here in white. How about that? A typical element of this looks like GI-NI. Right. Because a typical element is a product of a bunch of these stupid cosets, right? And this is F of the sequence of GI. And so everything's covered. Right, because each one of these GIs goes, remember how this works, GI goes to GI-NI. Does that make sense?
Yeah.
Okay, other questions?
The figure 3.4.9 there, the very end, it's like if only each FI is what?
One-to-one and onto, but actually you could state it more generally. Each FI is one-to-one. F is one-to-one if and only if each FI is.
Oh,
F is onto if and only if, I very sloppily stated that. F is onto if and only if each FI is, and so you can put them all together there. Okay, so when I think of like groups that are sort of master of all this shebang, I think of two kinds of groups: permutation groups and free groups. How many of you have ever heard, we're going to get to this there, Mike, but how many of, I think I might have mentioned it, that every group is contained in a permutation group? Maybe you've ever seen that. It's a famous theorem, and we'll talk about this more later, but it turns out if I walk up to you on the street and give you any group, finite or infinite, it can be construed as a subgroup of a group of permutations. Basically, you just look at the actions of the group on itself and they give you permutations. The way the proof works is not very efficient because, for example, usually the way the proof works is it embeds a group inside a permutation group that's way bigger than it has to be in some cases, right? I mean, in general, you might need one that big, but the important thing is any group is a subgroup permutation group. We'll talk about that later. Free is kind of a dual notion in the following sense. We're going to see that any group is the homomorphic image of a free group. So if you have a group, you can put it inside a permutation group out there somewhere. On the other hand, there's some free group that maps onto that group. And free groups, I think I like the terminology here. It's very suggestive. Free means free. It's got no restrictions. The only thing it's got in a free group is generators. There's no relations on it. So let me try to make a little bit more precise what I have for what I've said. Definition. Let X I'll index my set by another set, but it'll be convenient for me to use both of them. We say X is a letter. I've used this word before, but I'm going to write it down a little bit more concretely. a word. Now, what do you use letters for? You use them to make words, and that's what we're going to do. Is an element or a symbol, if you like, of the form. So I'm going to start primitively. xi1, epsilon1, xi2, epsilon2, epsilon k. Where each xij is a letter from x. And the epsilon i's are equal to plus or minus 1. Okay. So that's what I'm going to mean by a letter in a word. So for example, before I pass to the next definition, let me give you an example. If let's make it easy. Let's suppose that I have just 3 letters, my set, if you will. What's a typical word look like? Well, and actually, I'm going to also add this symbol here, E, the identity. I'm allowing these words to have exponents of plus or minus 1. I can also take them all to be 0. You can think of it this way, but I'll just add this extra word, the identity, the empty word, if you will. It's, you might think of E, the identity, as the word with no letters, so it's empty, right? So when you add that letter to another word, it doesn't change it, right? What does a typical word look like? Well, one was the identity, of course, but let's do something that's not the identity. X, Y, X, E, X inverse, Y inverse, X, E inverse, Y inverse, X, Y inverse, Z, Z, Y inverse, anything. It's just, I have basically in this case 6 tools at my disposal plus the identity, and the letters I can use are every element in its inverse. So there's 6 things I can use. I used them all here. This is what a typical word may look like. Now, there is a way that we can shortcut this a little bit, right? I can use the symbol 2 to notice that I can cancel that out. And then Y, X, Z, X inverse, Y inverse, X, Z inverse, Y inverse, X, Y inverse, X, Z, X, Z cubed, Y inverse. So I can shortcut this a little ways, right? To make it a little bit more pleasant. Or if I had something like this, something else that I'll allow us to do here is when I see these 2 next to each other, I'll cancel that down to the empty word or the empty letter, the identity, and that would cancel further. ZZ. Let's see what else I got. XX inverse cancels, and then the YY inverse cancels. XX inverse cancels, YY inverse cancels. And I wonder if I've got anything else. Let's just take one more step. Z squared, X, and then all this jump in the middle is canceled, Z inverse, X. So I'm gonna allow two types of canceling. Number one, I can write integer powers either positive or negative when I see powers of the same thing together. And I'll allow getting rid of things when opposite power. When opposite powers of the same element encounter each other. So let me add to this. Often my word in reduced form and you can always reduce to this form. That's one A1, X2 A2, X AK. Where I1, well, let's say I sub M is not equal to I sub M plus 1. Right, so no two indices next to each other together, and the AIs are in fact in Z. Notice that this particular one picks up the identity because you can take all of them to be 0. So that's where I'm going to be reduced form, and that example I think kind of illustrates what's going on there. So let me give you a theorem. Let X be a set. Let X be a set, then some number of Fx or, and this is the group generated by the X, is a group under multiplication. And my operation here on my set of words is I'm going to stick the words together to make bigger words. F O and of course, I hope it's clear what I mean by the operation here. So if I take this white element times this element here, A times B, I would just stick this Z squared on the end, or this Z squared XZ inverse XZ on the end. And in the other order, I will put it here. Notice you would get different elements here. And I put larger in parentheses because, of course, it's possible to join two words and have a whole bunch of canceling out, maybe even down to the identity, right? Here is kind of a cool example. Suppose I look at all words that I can form just with the letter A, right? Well, notice that everything is reducible down to a power of A. So this is a set of A n Z. So this is actually isomorphic to Z. So the moral is the free group on one element is abelian. It's a big abelian cyclic group. If X equals the set X equal X Y is non-abelian. Because XY is not equal to YX, by definition, it's free. Right, we say two words are equal if they read the same with respect to their letters. Notice that if X is a free group on a set of one or more elements, every element has infinite order. The next time I'm going to do theorem 354, you might have a look at that. But what it says is the free group is a solution to a universal mapping problem. Once again, we've got this mapping problem coming up, and this is where we're going to get that every group is the homomorphic image of the free group. Okay, that's a good place to stop. Any questions? Any questions? All right, well, you all have a good one, and I will see you about Wednesday at least. See y'all later.